Hello students, this is the second chapter and second session of your course MSE230, which is discussing about atomic structure and interatomic bonding. The slides are taken from those prepared by Wiley based on the textbook and what I have gathered. This chapter is a review of what you have learned before in general chemistry courses like CHM 115. Why in chapter 2 we study structure? The reason is because some of the material's properties are determined by an atom's structure. You know, an atom consists of very small nucleus having protons and neutrons and is surrounded by moving electrons. The number of protons define the atomic number. Say hydrogen atomic number that has only one proton in the nucleus is 1. Atomic mass is defined as 1/12 mass of carbon, and atomic weight definition is given here. Based on this atomic weight of carbon is 12.011 and its number is 6. Its atomic number is 6. How electrons surrounding nucleus is discussed by different models. One is Bohr model, and a newer one is wave mechanical model, in which electrons have wave-like and particle-like characteristics. Two wave-like characteristics are electron position in terms of probability density, and the second one is quantum numbers. Quantum number determines shape, size, orientation of probability density. Energy level is separated by subshells. Subshells are consisted of orbitals. Shell numbers usually denoted by these letters K, L, M, N, O, or numbers 1 to 4. And subshells are shown by letters S, P, D, and F. A question: what is the difference between subshell and orbital? How these orbitals look like in a 3D space is shown here. In S orbital electrons commonly, we have maximum two electrons circulating in this space, and in S orbital electrons commonly located with spherical regions. The P orbital is similar to a dumbbell shape as shown here. So we see these dumbbell shapes shows the probability of electrons spinning in this dumbbell around this dumbbell shape. This dumbbell is along x-axis, and there are two other dumbbell shapes along y and z axis as shown here. We can discuss this in the class more. How electrons are arranged in these layers and orbitals for each element is known as electron configuration for that specific element. An example is the electron configuration of oxygen. Oxygen atomic number is 8, therefore there are 8 electrons. On the first layer we have only S subshell, so the first 2 electrons fill it. We use arrows to show each electron, and there's a question: why arrows pointing in different direction? So that's one question. The other one is so we are done with these first 2 electrons. The other 6 that are left, the second 2 electrons fill in the next level of energy. So now we jump from level 1 to level 2. So it goes to the next level of energy in the second shell, which is, and of course the subshell of the shell, which is 2s orbital. The next level is 2p. and we have so 2 are filled here, so we have another 4 as you can see here. So we have left with 4 electrons. We start to occupy each cell by 1 electron, so this one, and this one, to occupy the lowest available energy state. After we are done with the first electron, now we insert the second electron in the cell. Therefore, 4 electrons are filling 2p orbitals, leaving the overall configuration as 1s2. As you can see, 2s2 and 2p4. What if we want to write down the electron configuration for O2 minus, which means an oxygen atom, which has donated 2 of its electrons. What if we have larger atomic number? How we can perform electron configuration? First, we need to know the electron energy state for different subshells in shell numbers, as electrons tend to occupy lowest available energy states. So they find the lowest available energy state from here. They fill this level, then they jump to the second one, third one, and it's interesting, then third that has 3 orbitals, S, P, and D. The first orbital of fourth one has lower energy, so this one will be filled earlier than 3D. Of course, as you know, we can fit only 2 electrons in each of these orbitals. This is also indicated in figure 2.6 on page 23 of the text. Expected electron configuration is listed here. This is based on what we discussed in the previous slide. A more complete list can be found in page 25 of your textbook table 2.2. Let's do this. Find in electron configuration, the electron in outer unfilled shells, named as valence electrons, are available for bonding and tend to determine an atom's chemical properties. An example is given here for carbon with atomic number of 6. The valence electrons are those in the second shell. So these element, so this element needs 4 more electrons to have its second shell filled and become stable, because when we are fitting these 6 electrons, we are done with 1s2, 2s2, so far 4, and we have 2 more left, so we will only have 2 electrons filling 2p orbital. We need to have another 4 electrons to fill and make it a stable atom. Valence electrons are shown here. Now let's find electron configuration valence electrons for an element that has higher atomic number, like iron, that has atomic number of 26. First, we arrange various shells and subshells according to their energy level, as we discussed before. The first 2 electrons fill 1s, then 2s, another 6 2p, another 2 3s, and then 6 and 3p, and we have another 2 for 4s. So far we are done with 20 electrons. 6 are left, so we start to fill the next 5. Each of these orbitals 1, and 1 more left, so this orbital will be full. Now we have 4 more available orbitals that are half. So we can write in the electron configuration, as you can see, starting from 1s2 to finally 3d6 comes before 4s2 when you write it down. Actually, these 8 electrons now are called valence electrons. 4s2, sorry, 4s2 belongs to the outer shell, fourth shell, and 3d6 also is unstable, so it's also ready to do chemical bonds. So that also consists of valence electrons. Okay. All the elements have been classified according to their electron configuration in this periodic table. As you can see here, this periodic table is also available in page 26 of your textbook. Here the elements are situated with increasing atomic number in 7 horizontal rows. Each of these rows are called periods. The arrangement is such that an element that all elements rate in a given column, like these elements or these elements, have similar valence. So they have similar valence electron structure. They also have similar chemical and physical properties. These properties change, of course, gradually, moving horizontally across each period. So from moving from left to right, these properties are changing. Here the first left hand side rows tend to lose electron, become stable, so they are called electropositive elements. And the other side, this row, because they intend and they like to receive electrons, they are called electronegative ones or electronegative elements. As an example, lithium tends to lose one of its electrons and then have the electron configuration of helium, which is stable. Generally we have in the left hand side metals and on the right hand side non-metals elements. The tendency of an atom to attract a bonding pair of electrons is known and is measured by electronegativity, which ranges from 0.7 to 4 for different atoms. Those that have a tendency to acquire electrons, they have larger electronegativity, and those who like to lose electrons, they have smaller electronegativity. I think this is good for this session. Thank you.